XRY, which mimics what we did here. Okay? That's just the notation we'll use. And as you'll see, this makes some definitions that we'll get, well, right now, a lot easier. Okay, so one of the most important definitions you'll get in this class, a relation R on a set X. So that means, remember, the ordered pairs, both of them are in X, right? So for a function, that's not true, right? For a function, this really is, unless the function happens to be from X back to itself, this is a relation on X cross Y, and X and Y are different. What about the order? Is this a relation on a set cross itself? Yes, right? Because each of these is a real number, or originally in an ordered field, but it's the same set here. This is in the same set as that. In a function, this and that could be and usually are in different sets, right? It's only an unusual situation where the function happens to go from the set to itself. All right? So we're going to only consider for this definition a relation on X. That means both things are in the set X, so it's similar to what happens here. Is called an equivalence relation if the following are true. Okay, so we have three conditions. The first one is called the reflexive property. And the nice thing about these definitions is they're all either things that you have heard of before, or words that you've heard before in some mathematical context, or they kind of suggest what they mean, okay? So the reflexive, well, you think about looking in a mirror, right? What do you see? You see yourself, okay? So this is saying that this acts like a mirror in the sense that X is related to X for all X an element of the set. Okay? So everything is related to itself. The next one, symmetric. This says if X is related to Y, well, if you know anything about what symmetry should mean, what should be the conclusion here? Yeah, Y is related to X. Okay, that's symmetry. And transitive, anybody got a suggestion for that?
X related to Y, Y related to Z, then X related to Z.
Okay, you're right, except there was a word at the beginning that either you didn't say or I didn't hear it, which is important. If.
Yes.
Okay, maybe you said it and I didn't hear it. Okay, well, if I didn't hear it, maybe somebody else didn't. But the reason I'm emphasizing that is that this one is a completely different kind of a statement from this one and this one, okay? These are both if-then statements. This is something where you pick up an X and you make sure that it's related to itself. This one, you're assuming that X is related to Y, and you have to prove that Y is related to X. Yes?
Doesn't the reflexive property just come from the symmetric property if you just have...
Actually not, nope. There are circumstances, if you throw in transitive, so some of these can be derived under the right circumstances, okay? But there are examples, and we'll see examples where any of these two can be true and the third is not true. So you actually do need all of them. That's a good mathematical instinct, okay? You know, check up on your prof, right? Well, do we really need that? You know, okay. And I'm not just, you know, I didn't, that was my own tone, right? Okay, but it was a good comment, okay? Because we're trying to be lazy in here, right? And we don't want to have to learn anything that we don't have to learn, okay? Right? So great question. And the answer is we got to have all of them because there are examples of relations that satisfy any two of these but not the third. Okay, so you can't throw any of these away. Okay, so transitive, if x is related to y and y is related to z, then x is related to z. Now, of course, you can play games with this, right? Because once you have the symmetric property, then there are some automatic things, like what Eric was asking about. For example, you can fiddle with the transitive law, right? You can also have if x is related to y and z is related to y, then z is related to x. You can use the symmetric law to get all kinds of variations on this, all right? And we'll just do that, okay, in the future. We won't, have to prove any of those kinds of things. Okay, so the best way to understand something, again, is to work with it. So let's go back and look, okay? We won't really talk about functions in connection with this, although there is an exercise about it that you have to do, so enjoy, okay? But generally, a function isn't even going to be applicable here, right? Because it goes from one set to another. So the only time you could even consider it is when a function goes back to the same set. And one of your exercises is to understand exactly what happens in that situation, and it's not very interesting, so we'll move on. Okay, and leave you with the exercise. So what about order? Okay, let's go through these. Is it reflexive? These are real numbers now, right? Order is on, right? This is on R. Is it reflexive?
It's related to itself by quality.
Sorry?
Is it related to itself by quality? Is that
This is my relation. So the question is x less than x for all x an element of R? No. Okay, so that's easy. So again, the point is to really write down the definition and think about it. Okay, now if the answer is no, what do we have to do? We have to come up with a concrete example. We don't have to, but that's usually the best way to do it. Yes?
Is that less than or equal to? Or what is that?
It's a less than.
It looks like you have equal to in parentheses there. What's that?
This is equivalent. That's a double arrow. Where?
Keep the notation going is what I thought you were doing. Since you double arrowed above with notation.
Also double arrow. Oh, I'm
just thought you were
confused.
continuing that it's a notation issue.
yeah, it was.
I was, yes. Okay, no, we'll talk, I mean, that's a good question also. We'll talk about less than or equal to in a minute, right? But I'm considering this particular relation, right? And the answer is no, and so it is not true that 1 is less than 1, okay? So, here's the thing to remember. When you're doing an exercise, and you're going to have some of these, right? And you're trying to find out, is it, is it transitive? Is it symmetric? Is it reflexive? If it's not, it's easy. You just come up with a concrete example to show it's not. Okay? So there we have it. 1 is not less than 1, so we're done. That's the trichotomy, right? Okay, what about symmetric? No. Okay, so give me an example.
1 less than 2, 2 not less than 1.
Yeah, 1 is less than 2, but is not 2 less than 1. Okay, so it's not symmetric. Transitive. Why is it transitive?
1 less than 2, 2 less
Oh, careful, careful, right? A couple people did this on the test.
Give an example.
You can't prove something with an example, but this was actually an axiom, right?